Hi everyone, welcome to this tutorial. Today we're going to look at formula of compounds. Before we start on this topic today, first of all, we have to understand the meaning of the word compound. In chemistry, a compound is any substance which consists of two or more elements chemically combined. And one of the uniqueness of a compound is that a compound must have a chemical formula. For instance, this is a compound, H2O, water. HCl is a compound. C6H12O6 is a compound. So these are chemical compounds. A compound is a substance which consists of two or more elements chemically combined. In the case of water, you are seeing two parts of hydrogen to one part of oxygen. That is two elements combined in water. In the case of HCl, you're seeing one part of hydrogen to one part of chlorine. In the case of glucose, you're seeing 6 atoms or 6 parts of carbon, 12 atoms of hydrogen, and 6 atoms of oxygen, 3 atoms combined together. So you see that every compound has a chemical formula. Now, we're going to the types of chemical formula. The first we see is what we call the empirical formula, which I can call EF. We have another one called the molecular formula, which we can abbreviate as MF. Have a third one called structural formula, which means mainly in organic chemistry. Structural formula is also known as molecular structure. We have the fourth one called condensed formula. We also have the fifth one called skeletal or line formula. Some people also call it graphic formula. So these are the formula of a compound can possess in chemistry: empirical, molecular formula, structural, also known as molecular structure. Structural formula, also known as molecular structure, condensed formula, and then skeletal formula. Okay, now we're looking at these two formula, empirical and molecular formula. Empirical formula, from the definition on the whiteboard, is the formula of a compound which shows the atoms in one molecule of a compound in their simplest ratios. In their simplest ratios or smallest ratios. The molecular formula is the formula of a compound which shows the actual number of atoms, present in one molecule of a compound. So let's look at the two definitions, because these are two types of formula, molecular and empirical, are directly related. So how do we explain that? So let's look at the substance called glucose. Whose formula is C6H12O6. So this is the molecular formula of glucose. What it means is that in one molecule of glucose, we have one molecule here. In chemistry, we say that a compound is one molecule when there's no number in front of it. The coefficient of glucose here is 1. I don't have to put 1 here. But if I put 2, I'll call it 2 molecules. So in one molecule of glucose, we have one molecule of glucose consists of 6 atoms of carbon, 12 atoms of hydrogen, and then 6 atoms of oxygen. So the actual number of atoms of carbon in one molecule of glucose is 6. The actual number of atoms of hydrogen is 12. The actual number of atoms of oxygen in one molecule is 6. That is why the molecular formula of glucose is H12O6. That is the formula that shows the actual number of atoms present in one molecule of a compound. Then, how do we now get the empirical formula of glucose? The empirical shows the atoms in their smallest ratio. What do? What we do is, we're going to break down these numbers. Carbon is having 6, hydrogen is having 12, oxygen is having 6. break them down to their smallest ratios. The highest common factor of 6, 12, 6 is 6. Divide them by 6 all through. What divided by 6 all through, we have 1 is to 2 is to 1. So we reduce this atom to their smallest ratios, and that will give us the empirical formula of glucose. Now the empirical formula of glucose now becomes 1 carbon, 2 hydrogen atoms, and 1 oxygen atom. So you see that empirical formula is of smaller magnitude compared to molecular formula. Molecular formula gives the actual number of atoms present, empirical gives these atoms in their ratios. How are they related? If I have CH2O being the empirical formula, and multiply it by an integer, what number will I multiply this formula with to get C6H12O6? I'll multiply it by the number I use to divide is 6. So if I multiply this empirical by 6, 6 times 1 of carbon gives us 6, 6 times 2 of hydrogen gives us 12, 6 times 1 of oxygen gives us 6. Multiply it by 6, we get back the molecular formula. So what do we say about this? We can now say that empirical formula EF multiplied by a positive integer n will give us molecular formula, where n in this case is 6. If you open the bracket, you now get your molecular formula. So now we're looking at molecular structure, condensed formula, and skeletal formula. So molecular structure, otherwise known as structural formula, is the formula of a compound which shows the chemical bonds present in one molecule of the compound. The formula of a compound which shows the chemical bonds present in one molecule of the compound. For instance, we know that the molecular formula of ethanol is C2H5O6. That means in one molecule of ethanol, we have 2 atoms of carbon, we have 6 atoms of hydrogen, that is 5 plus 1 is 6, and we have 1 atom of oxygen. This is the molecular formula of ethanol. But we're trying to look at what's called molecular structure, otherwise known as structure formula. Now, to get the molecular structure of ethanol, I have to draw the ethanol structure, showing the bonds present in ethanol. So this is the molecular structure of ethanol, otherwise known as the structural formula of ethanol. Another example is this compound called butane in chemistry. This is the molecular formula of butane. Now, in one molecule of butane contains 4 atoms of hydrogen and 10 atoms of hydrogen, 4 atoms of carbon and 10 atoms of hydrogen. So to get the molecular structure of butane, I have to put the carbon atoms in a straight line and show the bonds present in this alkane. So this will now give me the molecular structure of butane, C4H10. You count it, you have 4 carbon and then 10 hydrogen. You count this one, you have 2 carbon, then 6 hydrogen atoms, 1, 2, 3, 4, 5, 6. 5 plus 1 is 6, and then 1 oxygen atom. So these ones are called molecular structure or structural formula. Then we go over to condensed formula. Condensed formula. As we discussed, ethanol is C2H5. This is the molecular structure of ethanol. The condensed formula of ethanol will be CH3, CH2OH. Condensed formula, whereby we take the first carbon bonded to 3 hydrogen, that gives the methyl group. The second carbon bonded to 2 hydrogen, that gives you the methylene group, and then the OH. This is condensed formula of ethanol. Then for butane, which is this, the condensed formula of butane, you can still write it. It's a very simple thing. illustration, we have the first carbon bonded to 3 hydrogen, that gives us CH3. Second carbon bonded to 2 hydrogen, CH2. Third carbon with 2 hydrogen and that methylene group CH2. Then fourth carbon with hydrogen, that is CH3. So this is the condensed formula of butane. We can say write this formula as CH3. Since the methylene group occurs 2 times, we can write CH2 bracket and then 2 outside, ensuring that repeated itself 2 times and then CH3. The 2 are implying the same thing. So we now go to skeletal formula. Skeletal formula of ethanol. Okay, how do we go about it? Okay, on the whiteboard you can see these 2 compounds, the molecular structures or their structure formula. This compound is called butane, as we described earlier on, while this compound is called propanol or propan-2-ol. Underneath is the skeletal structure of propan-2-ol, the line formula. You can see what does this imply. At this point here there is carbon. At this point there is carbon. At this point those are under carbon. So look at it. This point represents the carbon that is here, that is bonded to 3 hydrogen. This is the single bond. There is carbon at this point of intersection with the carbon in the middle, bonded to hydroxy group. And there's another carbon at the extreme, bonded to 3 hydrogen. This line here represents the single bonds in the structure. So we call it the skeletal formula of propanol or propan-2-ol rather. Then this one, this is butane. This is the molecular formula of butane, C4H10. Then look at it. You see that this is the skeletal formula of butane. If you count the points, number 1, number 2, number 3, number 4. So there are 4 carbon atoms in butane. So that is the skeletal structure of butane. In the skeletal structure, we don't show hydrogen, please. We can show any other substituent group like hydroxy group or any other functional group. So this is butane. Here, first carbon going with 3 hydrogen, second carbon here going with 2 hydrogen, third carbon going with 2 hydrogen, and then fourth carbon going with 4 hydrogen. Just like when you have this in chemistry and you ask which compound is this? This is a similar structure, it's not a rectangle. This is called a cyclobutane because you know that butane are alkanes. Alkanes are known by having single bonds. Alkanes have single bonds. So this is called cyclobutane. There is an alkane that has 4 carbon atoms, but cyclo because it's in cyclic form. Okay, so now we are now going to the calculations on empirical and molecular formula. Okay, now we're going to the calculations on empirical and molecular formula. Before we go to that, first of all, we have to look at how to calculate percentage composition of elements in a given compound. Because before you go to the calculation on empirical and molecular formula, you have to know how to evaluate the percentage of elements in a given compound. Look at this question on the whiteboard that says calculate the percentage composition of glucose. If I start solving this problem, I'll first of all ask myself, do I know the formula of glucose? Do I know the molecular formula of glucose? Yes. Glucose is C6H12O6. When you have done that, you have to find the relative molecular mass of glucose. To calculate the relative molecular mass, you're going to add up the relative atomic mass given to you in bracket. So the atomic mass of carbon is 12, and there are 6 atoms of carbon. Now say 6 times 12. Since one atom weighs 12 grams, 6 atoms have become 6 times 12. For hydrogen, I have 12 times 1. And then for oxygen, I have 6 times 16. When I calculate this, I'm going to get 180. So I'm trying to find the percentage of each element in this compound. Then I'm going to find the mass of carbon in glucose. Mass of carbon is going to be 6 times 12. So 6 times 12 gives us 72 grams of carbon in glucose. So percentage of carbon will now be mass of carbon all over relative molecular mass of glucose times 100 over 1. And that will give me carbon is 72 over 180 times 100. And that will give us 40%. So this is the percentage of carbon. Is it 40? Let me verify the answer of carbon in glucose. So this is that's right, 40%. So this is the rate of carbon in glucose. So carbon is giving us 40% in glucose. So we now go to the next level, which is hydrogen. To find the percent of hydrogen, we have to find the mass of hydrogen instead of carbon. Hydrogen now hydrogen is 12 atoms, 12 times 1. The mass of hydrogen is 1, that gives us 12 grams. So the percentage of hydrogen now becomes mass of hydrogen. We change the carbon to hydrogen all over the molecular mass of glucose times 100 over 1. To do that, we now get 12 over 180 times 100, and that will give us 6.67%. So hydrogen is giving us 6.67% of glucose. The next element there is oxygen. We still have the molecular mass of glucose on the board as 180. We now find the mass of oxygen in a compound. All that becomes 16 times 6. 16 is the atomic mass of oxygen, and there are 6 atoms. That gives us 96. So the percentage of oxygen becomes mass of oxygen all over molecular mass of oxygen, please, all over molecular mass of glucose times 100 over 1. So the mass of oxygen in the compound is 96 grams all over 180 times 100 over 1. That gives us 53.3%. So oxygen gives us 53.3%. So if you add all the percentages of the 3 elements in the given compound, in any given compound, not only glucose, if you add the percentage composition of the elements they give up, you must get 100%. Add up all this, you must get 100%. Any compound, the sum of the percentage composition must be 100%. Now we'll go over the calculations on empirical and molecular formula proper. Okay, we'll look at the problem on the board on empirical and molecular formula calculation. It says a carbohydrate contains 40% carbon and 6.67% hydrogen. Given that the molecular mass is 180, calculate number 1 the empirical formula, number 2 the molecular formula of the compound. And we're given the atomic mass of carbon as 12, hydrogen 1, oxygen 16. So we're going to go to the first question, the empirical formula. So how do we solve this problem? How do we solve it? We're going to do it step by step. The first thing is you list the percentage of the elements in the compound. The elements in the compound are carbon, hydrogen. Carbon is 40%, hydrogen is 6.67%. Before you go ahead to solve, you ask yourself, the sum of this percentage on the board, is it not 100%? If it's not 100%, then you're going to think of what to do. If you add 40 plus this, you get 46.67%. So that means the compound is not complete. As I told you when I did percentage composition of a compound, I said that some of the percentage must give 100%. If not 100%, you have to think that something is missing. So, and if you have a good knowledge of chemistry, a carbohydrate contains 3 elements, or even from here, this is a kind of hint to tell you that the element that is missing there is oxygen. So, carbohydrate contains carbon, hydrogen, and oxygen. And the word is like carbon hydrate. Carbon hydrate means water. Carbon and water join together. So there's oxygen in water. So we have to write oxygen, and we have to find the percentage of oxygen not given to us. How do we find it? We'll call it S. S, we'll add these 2 and subtract from 100. So will be 100 minus 40 plus 6.67. So you add up these two as 100, you're going to get 53.3%. That's the percentage of oxygen. The next thing you do is you divide the percentages by the relative atomic mass of each element. Divide 40 by 12 for carbon. Divide 6.67 by 1, that is hydrogen. Divide 53.3 by 16, that is for oxygen. When we divide this, we're going to get 3.33, 6.67, 3.33. So having done that, you move over to the next step. The next step is you divide the first step, second step, as it's being videoed, you can see it on the board. The first step, you do the percentage. Second step, divide the percentage by the relative atomic masses each, and you get these values. Third step, you divide the values you obtain in this second step, divide again with the smallest ratio. The smallest ratio among them, 3.33, 6.67, is still 3.33. So divide all of them by 3.33 and approximate the nearest whole number. So when you divide all of them by 3.33, you get 1, probably 2, and then 1. So the empirical formula of glucose will now be in the ratio 1:2:1. We'll now write of the carbohydrate, which I presume is glucose, is C, that is 1 carbon, the hydrogen is 2, and then 1 oxygen. So this is the empirical formula of glucose. So you see, I can find the empirical formula of any compound using the percentage composition. Pause. So we now go back to the second question of find the molecular formula of the compound. Already, before you go to molecular, you must first of all get your empirical formula. So we obtain the empirical formula CH2O. When I go into the molecular formula of the compound, so what you do is you multiply the empirical formula by the integer n, a whole number which you are going to look for, and equate this expression to the relative molecular mass of the compound. So we'll do this. In bracket, we place CH2O n equal to the molecular mass. So you have to find the molecular mass in the equation. You go to the equation, you see where they wrote the molecular mass or molar mass is 180. You write 180 here. Then how do you evaluate n? You're going to find the molar mass of the empirical formula for a solve for n. So you now go down. Carbon, you take the atomic mass of carbon as 12 in bracket. Hydrogen is 2 times 1, 2 atoms, and the mass number of carbon is 1. While oxygen is 16 for 1 atom, then multiply by n equals 180. Solving this, 12 plus 2 is 14 plus that is 30, and I have 30n equal to 180. My n becomes 180 over 30. That will give you a definite whole number, 6, an integer. So your n is 6. That's the whole number you're looking for. Then when you have done that, you go back to this expression, EF times n. And remember that your EF is the empirical formula. So which is CH2O multiplied by n. That n is 6. You open the bracket. So 1 carbon inside times this gives you C6. 2 hydrogen times this gives you H12. The 1 oxygen times gives you O6. So this is the molecular formula of the substance, which is actually glucose as predicted. So we are going to look at the second problem here. An organic compound contains 52% carbon, 13% hydrogen, and the rest oxygen. Given that the vapor density is 23, calculate this molecular formula. To solve this problem on the whiteboard, we have to find the molecular formula, but we know that before we go to molecular formula, we must first of all find the empirical formula of the compound. So we're going to have carbon, hydrogen, and the remainder is oxygen. So we have to first start by getting the empirical formula. Carbon is 52%, 13%. And as I told you, to find this one, you add these two and subtract from 100. Call it S, which is 100 minus the sum of 52 plus 13. Now give us 35%. The next step, as if you have been following the video, the next step is you divide these percentages by the atomic masses. Now carbon is 12, this one is 1, oxygen is 16. Give you 4.33, 13, and 2.17. Then the next step is to divide these values with the smallest of them all. The smallest is 2.17. So divide this by 2.17, 2.17, 2.17. Will give you approximately 2, approximately 6, and approximately 1. So the empirical formula of this compound will now become C2H6O. So that's the empirical formula of this compound given on the board. Then we are going to molecular formula. So we now move to molecular formula. I repeat myself, to get the empirical formula, you need the percentages of the elements. This was not given to us initially. You have to subtract the sum of these two from 100. Get at 5. Then divide the percentages by the relative atomic masses. You now have these values. Then out of these three values, the smallest is 2.17. Then divide all of them again by 2.17. You now have the ratio 2 is to 6 is to 1. Give carbon 2, hydrogen 6, and oxygen 1. You get the empirical formula. We're now going to the molecular formula. To get molecular formula, as we usually do, multiply the empirical formula by an integer n and make it equal to the molecular mass of the compound. When you look at the question properly, you see that we are not giving the molecular mass of the compound. They gave us what they call vapor density. We know that the relationship from gas laws, relative molecular mass is given by 2 times vapor density. So you're not going to work with 23, you have to get the molecular mass first. You now have 2 times 23, that gives you 46 as the molecular mass. You go back to this formula, the empirical formula we got as C2H6O multiplied by N equal to 46. So having done that, we now have 12 for carbon, 6 for hydrogen, and then 16. Replacing these values by the actual atomic masses multiplied by N equal to 46. So you add everything, we're going to have 46 and equal to 46. Everything here will give us 46. 24 plus 6 is 30, then 40 plus 6 is 46. So M becomes 46 by 46. That gives us 1. So since N is 1, that means we go back to this expression and replace N with 1. So now replace N with 1 and expand the expression. 1 have no effect, definitely. 1 times will give you 2. This is 6. And there was also 1. So that means the empirical formula and the molecular formula can be equal when N is equal to 1. So this is the molecular formula of the substance. So having done that, what then do we do? We can predict, we can ask you to draw the structure of this compound. This compound C2H6. You try to put the carbon atoms on a straight line. Try to put a single bond on it. And then hydrogen is 6. You have 1, 2, 3, 4, 5, 6. The compound is saturated now already. So you now start wondering where are you going to put the oxygen? So, but we know that oxygen can never be, there's no place for it to stay now. So, but we know that oxygen can join to one hydrogen to make the hydroxy group. So we can have O and then H here, single bond. So we have a compound. This is that. This compound is called ethanol. Ethanol. Somebody else can also draw this for the compound. Have this. The compound of this is an alkanol, ROH in organic chemistry. While this one is also correct, CH is an isomer to this. So this is called methoxy. Methoxymethane. That's what this compound. Methoxymethane or dimethyl ether. Dimethyl ether. In the having the homologous formula ROR. You look at them, any of them works. So this is C2 H6, 1, 2, 3, 4, 5, 6, and then one oxygen. C2, 1, 2, 3, 4, 5, 6, and then one oxygen. So that is it. So move over to the next question. So looking at the question on the board, alazine C5H8NO5 with molecular mass of 284 is a new drug for treating malaria. That means its molecular formula. This question is straightforward. It's very straightforward and very simple. You look at it, this formula, this expression, by having N here, that means they have already calculated the empirical formula for us. We just walk straight. You don't need to find percentage of each element again. So we have bypassed the area of empirical formula. What we have to do is we equate the C5H8NO5. This is the empirical formula expression. Equate it to 284 and go ahead to solve to find N. So our carbon is 12 times 5, Habit is 8 times 1, and then plus, you add this. Also is 16 times 5 equal to 284. You solve 12 times 5 is 60, 8 times 1 is 8, 8 plus 6 is 68 times n, 68n plus 80 equal to 284. So 68n will now become 284 minus 80. 68n gives me 204. You solve for n becomes 204 over 68, and that will give us 3. So the chemical formula of the compound now becomes C5H8, replace n now with 3O5. So this is the molecular formula. Or as well, you can see expanding if you wish. Now C15, that 3 times 5. H24, 3 times 4, 8, and then O5, being the molecular formula of the compound. Okay, now we'll come to the last example for today's tutorial class. This one tells us that 20 grams of a hydrocarbon contains 17.14 grams of carbon and 2.86 grams of hydrogen. Calculate number 1, the percentage composition, number 2, the empirical formula, number 3, the molecular formula, given that the molar mass or the vapor density is 28. Okay, having done that, let's look at this. Let's start with the first one. The compound is hydrocarbon. I want to know in chemistry, a hydrocarbon is an organic compound that contains only 2 elements, which include carbon and hydrogen only. So the mass of the hydrocarbon, so number 1, mass of the hydrocarbon, let me call it Hc, is 20 grams. Hc presents hydrocarbon for me. Then mass of carbon in the hydrocarbon is 17.14 grams. We want to find the percentage of carbon in, also give us mass of hydrogen in the compound as 2.86 grams. So let's start by finding the percentage of carbon in the compound. So percentage of carbon in the compound now become mass of carbon all over mass of hydrocarbon times 100 over 1. And that will give us the mass of carbon is 17.14. The mass of hydrocarbon is 20 times 100 over 1. When we solve this, we'll get 85.7%. So we'll have 85.7% of carbon in the given compound. So similarly, we can still find the percentage of hydrogen. So the percentage of hydrogen in the compound will become mass of hydrogen all over mass of the compound, which is the hydrocarbon, times 100 over 1. The mass of hydrogen in the compound is given to us as 2.86. The mass of the compound is 20 grams times 100 over 1. When we solve this, we're going to get 14.3%. So to confirm our answer, we'll add the percentages together. Since the compound contains 2 elements, it's going to give us 100%. So having done that, we'll now move to the empirical formula of the compound. Going to the empirical formula of the compound, since we are going to the percentage composition, it's going to be easier for us now. So find the empirical formula. What we'll do is, the steps I gave you before, you need the elements and write their percentage composition. 85.7 here, 14.3 here. The next, you divide with the relative atomic mass of each element. As I told you before, you now have 85.7 over 12, 14.3 over 1. When you divide, you have 7.14 here, 14.3. The next step, divide again with a smaller value or smaller ratio. There are only two values here. So divide with a smaller value. You now have 7.14, 14.3. The smaller one here is 7.14. 7.14, 7.14 there. You get 1 and you get approximately 2. 1 is to 2, that's the ratio. Then you now assign these values to each atom. Carbon is only 1, ratio of 1. Hydrogen is 2. So this is the empirical formula of the compound CH2. So that answers question number 2. Going to number 3. Number 3 is we have to find the molecular formula. To find the molecular formula of the compound, we still follow the normal process. We have the empirical formula, multiply it by an integer n, which we're going to look for, and make it equal to the relative molecular mass of the compound. When you look at the problem, they did not give us the molecular mass, they gave us the vapor density. So, as I told you, the relationship between the two, molecular mass is 2 times vapor density, which is 2 times 28, 56. We'll come back to this, and I'll write CH2 bracket n equal to 56. When you have done that, then solve for your n. And I have 12 for carbon, 2 times 1 for hydrogen, using the atomic masses equal to 56. So 14n giving us 56. N is 56 over 14, that will give you 2. So when you have done that, you go back to the expression CH2 bracket n, replace n with, sorry, this gives us 4, not 6, 4. Replace n with 4. We now have CH2 bracket 4, that gives us C4H8. C4H8. This compound is otherwise known as butene. C4H8, butene. If you ask to draw the structure formula of butene or molecular structure, butene is an alkene. And alkenes are noted by having double bond. So you can put the double bond here, or you can put it here. So, and put the hydrogen atoms. Whenever you have a double bond between 2 carbon atoms, whenever you have a double bond between 2 carbon atoms, you abstract, you remove 2 hydrogen atoms and adjacent carbon. So there should be 2 missing hydrogen atoms here. So this is boot 1 in or 1 boot. You can still get boot 2 in. If you have to draw the skeletal structure of this compound, if you're in higher chemistry, you have this skeletal structure. There is 1, 2, 3, 4. 1, 2, 3, 4. There are 4 carbon atoms. 1, 2, 3, 4. And the double bond here, you now put the double on between carbon number 1 and carbon number 2. 1 and 2. Put the double bond here. So this is the skeletal structure of boot 2, or the line formula for boot 1 in, which is this compound. So, having done that, please always subscribe if you are watching this video and this video is of interest to you. Enjoy the lesson. Subscribe to our channel. Our channel still remains youtube.com/@bestsciencebrain. This is the moderator of the YouTube. channel, youtube.com/@bestsciencebrain. So if you watch this video and then you feel that it's okay, please subscribe. Go to our channel and then hit the bell there where you have subscription and subscribe, so the video can still reach out to people that require this knowledge. So now we're going to have another class very soon on the same topic. We're going to look at advanced chemistry for advanced aspect of this topic on combustion hydrocarbons. We're going to look at it in the next class very soon. Please keep watching. Thank you.